Okay, so today we are going to continue the series on gas laws, and we're going to talk about the ideal gas law, which is a way of combining all the empirical gas laws that we talked about in the last video into a single expression. So let's see how that works. The ideal gas, as we saw, we have a model for how gas particles, through the kinetic molecular theory, give rise to the observed properties that we saw for the empirical gas laws. So the particles are always in motion, pressure arises from the collisions of the particles with the walls of the container, and the average kinetic energies of the particles is proportional to the temperature. So if we also add the assumptions that the particles have no intrinsic volume, that is, the particles themselves don't take up any space, and that they also don't ever interact with each other, they just bang around off the sides of the container, then you have the so-called ideal gas model. So this is a way of just thinking about the particles that make up a gas of just particles. It doesn't matter what gas it is. If it's neon, if it's argon, if it's CO2, it shouldn't matter because the particles, to a very good approximation, have no intrinsic volume and don't interact with each other. And so this really works. Most gases, under the normal conditions that we measure them, behave more or less like ideal gases, to within a fraction of a percent of error. So it's an extremely useful way of thinking about the way gases behave. That's why we spend so much time developing it in this class. Of course, it's not actually right, and if you go to the right conditions, rather extreme conditions, you can see deviations. If you go to really high pressure, well, what happens is you push the gas molecules so closely together that the fact that they actually take up a little bit of space, remember it's a very small fraction of the total space taken up by a gas, less than 0.1%, but it's still not zero. And so that starts to make a difference at very high pressures and or at low temperatures. At low temperatures, the gas molecules aren't moving around very much, so they also get close together, and they spend more time close to each other, so they can start to feel that the forces between them really aren't zero. So they do interact with each other just a little bit, but it's not very much. It's not enough to cause a very large deviation under any conditions other than these rather extreme ones that I just mentioned. Okay, so the ideal gas law combines all the empirical gas laws that we were talking about into a single expression. If you were really tuned in during the last video, you may have noticed that there was some overlap between some of those empirical gas laws. And we always tended to hold two things constant and look at the relationship between two other parameters. And so that's exactly what we're going to look at today, is what happens when we put all of those together. And remember, the four things we talked about were pressure here, volume, moles, and temperature, and then R is a constant. So what we say here is the product of pressure and volume is equal to the product of moles times temperature scaled by this constant R, which is the universal gas constant. And so that basically works out to be this value in these units. And so most of the time when you're doing calculations with the ideal gas law, you need to take some time at the beginning to get your volume into liters. Your pressure needs to be in atmospheres. Moles are typically in moles, but you might be given an amount in grams, in which case you would need to convert to moles. And then temperature needs to be in Kelvin. And this last one is where students most often make mistakes. They forget that they need to convert from Celsius into Kelvin, and it actually makes a rather large difference, right? Because, for example, if you put 0 in here, you're going to get a very different answer than if you put in 273.15 Kelvin, which is the number you should put in. So you have to keep your mind on that. This second value here is just taking into account that liters times atmospheres actually has the same dimension as energy. If we convert that into joules, it changes the value of the constant. Doesn't change the meaning of the constant. The first value here is the one you're typically going to use in this class. Okay, so let's talk a little bit about the relationship between the ideal gas law and the empirical laws that we saw in the last video. You should be able to see that, remember, Boyle's law gave you a relationship between pressure and volume when moles and temperature were held constant. So now everything on the right-hand side is a constant. And I'm going to rewrite this for all the other empirical laws so that everything on the right-hand side is held constant as well. Charles' law basically said that volume over temperature will give us a constant, if we put everything on the other side, right? So if we hold moles and pressure constant, okay, volume, the ratio of volume to temperature is a constant, okay? And then Avogadro's law said that the ratio of moles and volume is constant. And so that would basically mean that we had pressure over RT. And when pressure and temperature are constant, then moles to volume, that ratio has to be a constant. And then the last one was Amundsen's law, which said that the ratio of pressure and temperature is constant when moles and volume are held constant. Okay, so all of those things are actually special cases of the ideal gas law. And so it means that we can still use all those handy ratio-based comparisons for doing calculations because they all come from the same ideal gas law. Okay, there's just a couple more points to get across, which is that standard temperature and pressure, that's something that's going to come up a lot. That's 0 degrees Celsius and 1 atmosphere of pressure. So 0 degrees Celsius expressed in Kelvin is 273.15 Kelvin. Another thing that is a handy number to remember is that if you want to know the volume of 1 mole of gas at standard temperature and pressure, you can just plug in 273.15 Kelvin, 1 atmosphere, and 1 mole, and solve, and you will find that it is 22.41 liters. That's the volume occupied by 1 mole of an ideal gas at standard temperature and pressure. And that can be a handy number to remember later on when we need to do some calculations. It can sort of shortcut you into the calculations. Okay, so now let's get into some examples. This is an example, pretty standard that you might find for calculation. This is how it might come up in a standard problem on your homeworks. All right, so we're given a weather balloon. It's got 30 kilograms of helium in it. Okay, you need to find the volume of the balloon near the Earth's surface where you've got the temperature and the pressure given. So it's pretty clear you should be using the ideal gas law. You've already seen volume, pressure, and temperature, and then of course you can get the moles from a mass of helium simply by using the molecular weight. The way I typically approach a problem like this is I start by just making a list of all the quantities I'm going to need in the right units. Okay, so if I have pressure, in this case, pressure is going to be 750 millimeters of mercury, but then I want that in atmospheres. So we're going to have that divided by 760 millimeters of mercury per atmosphere. And that works out to be 0.987 atmospheres. Okay, volume is going to be, that's our unknown, and it's going to be in liters. Moles, okay, so moles is going to equal 30.0 kilograms of helium times 1,000 grams per kilogram, and then we're going to multiply that by 4.0, we're going to divide that by 4.0 grams per mole. So 1 mole of that is 4.0 grams. It's 4.00 grams if we wanted to be more precise. And so that works out to be 7,500 moles of helium. And then the last one is the temperature, and like I said, this is the one that usually trips up students when they first do this stuff, but it's equal to negative 10.00 plus 273.15 Kelvin. So the way to handle degrees Celsius is you just add 2.73.15 to it. So this is going to be 263.15 Kelvin. Okay, so now we want to plug that in and rearrange to solve. And basically, you're going to get that the volume is equal to nRT over P. So that's going to be equal to 7,500 moles, 0.08206 liter atmospheres per mole Kelvin. 263.15 Kelvin, and then all of that over, basically over 1, but it's 0.987 atmospheres. And so when you crank all that through, you find a fairly large number, as you might expect. I got 1.64 times 10 to the fifth liters. Well, it's a weather balloon. Weather balloons are big. They have to carry a high payload up high into the atmosphere, and they use the lifting power of helium to do it. Okay, so that's a pretty standard example for a PV equals nRT calculation. Okay, another way that ideal gas law can be used that's not obvious right off the bat is that it can be used to express the relationship between density and molecular weight. Okay, so how does that work? Well, density equals mass per volume. So volume can be said to be mass per density, right? Just rearranging. And similarly, molecular weight equals mass per moles. You're used to these equations. So then moles can be replaced by molecular weight over mass. I'm sorry, mass over molecular weight. There we go. Right? We just switched the two things in the denominator. Okay, so working with that, now we can plug in and we can rewrite the ideal gas law in terms of these new things. So it's pressure times, we're going to replace volume with mass over density. And then we're going to replace moles with mass over molecular weight. We can always do this as just standard substitution by algebra. And now mass is in the same place on both sides, so it actually drops out. And we find out that an alternative formulation of the ideal gas law is that the ratio of pressure to density is equal to RT divided by the molecular weight. And there's various ways to write that. Sometimes you will see that the pressure equals the density times RT divided by the molecular weight. It's the same equation. Okay, so in this case, we have a question where we're being asked to find the density, so that's our unknown, of an unknown gas at a given temperature and pressure. And they want to know the molecular weight given the density. And so we can just plug this in, solving for the molecular weight. Oops, I should have made this molecular weight up here. Solving for the molecular weight, we have molecular weight equals density times R times T over pressure. And so I'm just going to plug these things in, converting as I go, right? The density is 3.101 grams per liter. Okay, so we've already got liters in there. Here we have 0.08206 liter atmospheres per mole Kelvin. The temperature was 15 Celsius. That's 288.15 Kelvin. I just added 273.15 real quick in my head. And then the pressure is 723 torr. And so if we divide that out, that's 0.9515 atmospheres. Okay? And working all that through gives us a molecular weight of 77 grams per mole. You can always go through, do your dimensional analysis, and cross things out. Liters cancel liters, atmospheres cancel atmospheres, Kelvin cancels Kelvin, and now grams and moles are the only thing left. So dimensional analysis works as it should for any problem like this. All right, the last context we're going to talk about, and I'm actually going to leave this problem for you guys to do as your discussion question, but I'm going to talk you through it at the beginning here, is how the ideal gas law can be used when we have reactions actually going on, stoichiometry. So here we have nitrogen and hydrogen, and we're going to consider their reaction to form ammonia at a constant pressure and temperature. And so that means we need to know the balanced chemical equation here, nitrogen plus 3 moles, so 1 mole nitrogen plus 3 moles of hydrogen is going to give us 2 moles of ammonia. You should be super familiar with that equation. Okay, so you could go through and you could calculate using PV equals nRT the number of moles that this value of this volume of nitrogen represents, and then go from there. But you don't actually need to if you think about it in terms of these two things being held constant. So that's a hint that I'm going to give you. And then once you've done that, you can do a PV equals nRT calculation to figure out what your yield is going to be if the reaction goes to completion. So you should work through these two things, and don't forget to convert to Kelvin and submit your answer as the